Okay, here's our solution to question 1. Now, the first thing that I've done, I've actually redrawn our circuit slightly differently to make it a little bit clearer about which resistors or globes are in parallel and which ones are in series. So I've labelled the globes A, B, C and D, and I'm actually reading the circuit this way. So we're looking at the direction that the electrons might travel. And so if we're walking around the path this way, here's our first junction. There's our first fork in the road. And so if we're coming around our circuit like this, there's our first junction there. Okay, so some of the current will pass through the 100 ohm resistor, which is I've labelled resistor B. That's resistor B. And the other part of the current will pass through these two resistors down here, the 50 and the 200. So that's resistors D and C. Both currents recombine here and return back to the battery. So all those currents recombine and pass through this final globe or resistor, which is resistor A, which is the 100 ohm resistor. So the currents recombine here and go through the 100 ohm resistor and return to the battery. So now let's look at which resistors are in series and which resistors are in parallel. Okay, so what we do the simple parts first. So hopefully you might see that these two resistors here, they are in series. And so we could simply add those together to come up with one single resistor of 250. Okay, and these resistors here are in parallel. And so to work out the total resistance there, we need to use the parallel resistance formula. So that will be 1 over RT equals 1 over R1 plus 1 over R2. So if I'm now going to work out the parallel resistance here, I would be going 1 over RT equals 1 over R1. Now it doesn't matter which one I call R1. I suppose I'll call this one R1. I'll call this one R2. So it's going to be 1 over 100 plus 1 over 250. So I now want to make those denominators common. So both of those will go into 500. So I could write this as 5 over 500 plus 2 over 500. And so therefore 1 over RT will equal 7 over 500. So to work out RT for this section here, this parallel section, I flip my fractions. So I flip that upside down and I flip this one upside down. So now I've got RT over 1 equals 500 over 7. And if I now reach for my calculator and work out 500 divided by 7, I get an answer of 71.43 ohms. So that means that this section of the circuit is behaving as if it's a single resistor of 71.43 ohms. Okay, so now finally the last section, the last two remaining resistors are these two here, and they are in series, so we just simply add them together. And so the final effective resistance of this entire circuit is going to be 71.43 plus 100, which equals 171.43 ohms. Okay, in this question, question 2, we have to calculate the current leaving the battery. Now, in our previous question, we determined that the total resistance of the circuit was 171.43 ohms. Now, in order to work out the current leaving the battery, we're going to use Ohm's law. V equals IR. Now remember that there are two versions of this law. There's the local version and there's the global version. If we wanted to look at the current flowing through one particular component of the circuit, then we'd use the local version. And when we're using the local version, V is the potential difference across the component, I is the current through the component, and R is the resistance of the component. On the other hand, if we need to work out something to do with the whole circuit, then we're going to use the global version. For instance, if we had to work out something to do with the voltage supply in the full circuit, in V, which is the battery voltage, would be what we're trying to find. Alternatively, we want to work out the current coming out of the battery feeding the whole circuit. Then we're trying to find I in the global version of Ohm's law, because in the global version, I is the current leaving the battery. And the other value, R, if we're looking at the global version, R is the total resistance of the circuit. So in this question, we have to calculate the current leaving the battery, which is this value, and we know the total resistance of the circuit because we calculated that in the previous question. And so we're going to be using the global version of Ohm's law. Ohm's law, V equals IR, but we want to work out the current leaving the battery, so I equals V over R. So that will be the voltage of the battery divided by the total resistance. So it's going to be 12 volts divided by the total resistance of the circuit, which was 171.43. So if I now work out that using my calculator, I get an answer of 0.0699, amps. Well, that's virtually 0.07. Now, often you'll find in a textbook problem or in an exam problem, rather than use such a low value for the amperage, they actually measure it in milliamps. And a milliamp is equal to 1 milliamp is equal to 10 to the minus 3 amps, or 1,000th of an amp. So we could also rewrite that answer as 70 milliamps. So that is the current that is leaving the battery. In questions 3, 4 and 5, we have to draw arrows showing the pathway of the current and electron flow. So here's our battery here. We know that's positive and that's negative, and we know that 200 years ago they took a guess and thought it was positive charges flowing through the circuit. So positive charges would move in that direction, and that became known as the direction of current. So that's the direction of our current. Later on, when they discovered the electron, they realized it was actually the electrons that were doing the moving through the circuit, not the positive charges. And so the electron flow is actually in that direction. Now, in the third part of the question, I wanted you to draw the pathway of the current through the circuit, showing how the current breaks up when it reaches the branch. So if this represents the current coming out of the battery, passing through that globe, now here's the junction. Now notice that this branch has a resistance of 100 ohms, whereas this branch down here, it has a resistance of 250 ohms. So it's going to be much more difficult. This is going to offer much more resistance to the current than our 100 ohm resistor. So the current will find it easier to go this way than in the other direction. So most of the current will go that way, and only some of the current, only a small part of the current, will go in this direction. But at this point here, they'll recombine, and the current will then go back into the battery. So what's really important to notice here is that if this current here is 0.07 amps, and let's just say for argument's sake, the amount flowing through this branch here was 0.05, then this here must be 0.02, because the amount of current flowing through this direction and this direction must add up to the amount that's coming out of the battery. And similarly, when they recombine, 0.02 amps is flowing down in that section, 0.05 is there, and when they recombine, it'll be 0.07. In questions 6, 7 and 8, we have to work out the current flowing through resistor A, B and C. So before we can do this, let's just summarise the key information that we know. We know the current coming out of the battery was 0.07 amps. And we know that all of that current will pass through resistor A. We also know that when it breaks up, some of the current will go this way and some will go this way. So now let's use Ohm's law, the local version of Ohm's law, to see if we can calculate the current through those three resistors. So now if we're going to look at resistor A or globe A, I'll just draw a diagram here. So there's a diagram which represents resistor A. We know that the resistance is 100 ohms. We also know the current flowing through that resistor or that globe is 0.07 amps. So we've just answered that question. So for A, the current coming out of the battery is all going to flow through resistor A, so that in fact is the current flowing through A. Okay, now looking at globe B. We need to know, let's see what we do know. If we're looking at globe B here, all we know is the resistance. We don't know the voltage across it. So let's see if we can work that out. Now we know, one thing we do remember, hopefully, that as the charges flow around the circuit, they will only lose energy when they flow across a resistor. And so the electrical potential at each of these points will be at 12 volts and 12 volts and so on. Now, if we knew what the electrical potential was here, and we knew what it was here, that would allow us to work out the difference in potential across this resistor. So let's see if we can work that out. If I could work out the voltage across this resistor, that would help me work out the voltages across the other resistors in the circuit, and we'll get to that in a moment. So I know that the current flowing through this resistor is 0.707 amps, and I know the resistance, so I can use the local version of Ohm's law to work out the voltage across it. the local version. So V equals IR, where V is the voltage across the component, I is the current through the component, and R is the resistance of the component. So it's going to be 0.07 multiplied by 100. And that will equal 7 volts. So we now know that the potential difference across this globe is 7 volts. Which tells us that if the coulombs of charge coming out here are at an electrical potential of 12 at this point, and they're going to lose 7 volts as they cross this resistor, then that means they're going to be, at this point here, they're going to be at 5 volts. So the electrical potential will be at 5 volts. Because the potential difference drop is 7 volts between here and here. We know that the green part in the circuit in here, because none of the charges have passed through any resistors yet, at every point in that green section, the electrical potential of the coulombs in that part of the circuit is 12 volts. They lose 7 volts as they drop through this 100 ohm resistor. So at the other side, they're now at 5 volts. And everywhere around here, they don't pass through any resistors yet, so their potential will be the same everywhere here. They're all the same electrical potential, which will be at 5 volts. On the other hand, if we look at the other side of the battery, of course they need to be at 0 volts by the time they return. So everywhere up to where they've come out of their last resistor, they'll also be at 0 volts. So 0 volts everywhere where it's yellow. So if we know that at this position here, for example, it's 0 volts, and we know over here in the red position, we know that it's 5 volts, then we know the potential difference across this resistor is 5 volts. So we know that potential difference across this resistor is 5 volts. So now we can work out the current through resistor B. So let's go ahead and do it using Ohm's law. Once again, because we're looking at an individual component, we're going to use the local version. So Ohm's law is V equals IR. But we wish to work out the current. So I equals V over R. And remember, we're using the local version, which means that I is the current through the component, V is the voltage drop across the component, or the potential difference across the component, and R is the resistance of the component. So in this case, it's going to equal the voltage drop across the component, which is 5 volts, and the resistance of the component, which is 100. So 5 over 100 is 0.05 amps, which we could rewrite as 50 milliamps if we wish to. So there's the current through globe B. Now in the last part of the question, we had to work out the current through the resistor C. So we can just use simple addition to work this out. We know that it was 0.7 amps coming out of the battery, 0.07, I beg your pardon. And we've just worked out that 0.5 amps is flowing through that part of the circuit, which means the remaining current, what's left over, must be flowing through this part of the circuit. And of course, 0.07 taken by 0.05 is 0.02. Now, the current through this branch will go through this resistor. So the current through the 200 ohm globe, or the 200 ohm resistor, is 0.02 amps. But because these two globes are in series, the current also flows through this resistor, and so the current through this one would also be 0.02, just in case we had to work that out. And remember, they will recombine here, so the current going back into the battery will be the same as the current coming out of the battery, which is 0.07 amps. Now, these remaining two questions should be quite straightforward because I think we've pretty much answered all of them. But let's go ahead and complete them. Question 9, we had to calculate the electrical potential at various points in our circuit. So you might remember in our last question we color-coded the different sections. So in this section here, this region in here, it'll all be at 12 volts, which includes section A. So A will have electrical potential, will be an electrical potential of 12 volts. After this resistor, after the current flows through resistor A, because we calculated it was a 7 volt drop, then the potential on the other side was at 5 volts. So everything in there, because it all remain at the same potential unless it flows through a resistor, so everywhere in the circuit in that region will be at a potential of 5 volts. So that includes points B, C, D and E. So B, C, D and E will all be at an electrical potential of 5 volts. We know that everything on the other side of the battery, right up until it reaches any of the resistors, so from there and all the way in there, because current going through this section of the circuit has not passed through any resistor before it returns to the battery, so in those sections it's all at 0 volts. So that includes sections J, H and I, J, H and G. So I, J, H and G are all at 0 volts. So the only one that's left remaining is point F. So let's have a look at how we can work out what the electrical potential is at point F. Okay, so we're now looking at point F. Now, you remember that the current flowing through this branch of the circuit from our previous calculations, so the current flowing through there was 0.02 amps. And it was also 0.02 amps through that resistor as well. So, let's see if we can work out the voltage drop across resistor C, and that will then in turn allow us to work out the potential at point F. So, we're now going to use the local version of Ohm's law one more time to work out the potential difference across this resistor. Because if we know how much electrical potential energy the coulombs lose passing through this resistor, we'll know where they're at, or what the electrical potential they have when they come out the other side. And that will be, of course, the value for F. So, the electrical potential difference, or the potential difference across resistor C, using the local version of Ohm's law, will be the current through the resistor, which is 0.02 amps, times the resistance of that resistor, which is 200 ohms. So, that will be 4 volts. So 0.02 times 200 is in fact 4 volts. We know the potential difference across resistor C is 4 volts, and I've redrawn those two globes over here to make it a little bit clearer. So let's just track one more time. We knew that A was at 12 volts. We knew that all this section in here is at 5 volts, including position E. So we know that the potential at that point there, the electrical potential is at 5 volts. Now we know it's going to lose 4 volts, or there's going to be a potential difference of 4 volts as the charges flow through the 200 ohm resistor. So by the time they come out the other side, they're going to be 4 volts less, which means at this point here, they'll be at 1 volt electrical potential. So position F will be at 1 volt, and if we had to, that would mean, because we know that the electrical potential over here is all at 0, then the potential difference across this resistor will be 1 volt. Now, you might remember that the electrical potential across resistor B was 5 volts. Well, guess what? The electrical potential across these two together combined adds up to 5 volts, which reinforces what I said in an earlier video. When you have two components or two resistors in parallel, or two parallel branches, the total voltage drop across both of those branches will be the same. So the total voltage drop down this branch across the single resistor in it is 5 volts. The total voltage drop across this branch over both of the resistors in that branch is also 5 volts. Okay, so now let's move on to the final question. Okay, in this last question, we are actually working out the voltage drop across resistors A, B, C, and D. And we've actually achieved that pretty much anyway, but let's go through and just finalize this question. So here's a redrawn version of the circuit showing what we've actually calculated so far. These are the currents that we worked out, and we'd worked out it was 4 volt drop across the 200 ohm resistor, and we worked out, because the same current's flowing through the 50 ohm resistor as is flowing through the 200 ohm resistor, we calculated that that would be 1 volt across there. Also, we knew that it was at 0 volts on this side, and it was at 1 volt here, so the difference must be 1 volt. Now, I did say earlier in the previous explanation that the voltage across here is 5 volts. Now, it's a law of parallel circuits that the total voltage drop across any branches in parallel will always equal the same. And so if these two here add up to 5 volts on this branch, then this will also be 5 volts. But let me just prove it also using Ohm's law. So we're going to use the Ohm's law, the local version of Ohm's law, to prove that the voltage drop across this resistor is 5 volts. So V equals IR, and we're using the local version. So the voltage drop across the 100 ohm resistor here will be the current through the component, which is 0.05 amps, multiplied by the resistance, which is 100 ohms, and that equals 5 volts, which is what we suspected. So hopefully these basic problems have given you a little bit more insight into solving problems in electric circuits, and there will be more to follow. So over the coming weeks, you should become increasingly confident with this sort of work. Thank you.